Dear students, welcome to the lecture number 6. So last time one student asked about some results on T1 spaces. So in this talk I start with some results on the T1 spaces. So here is the theorem which has two parts. It says a subspace of a T1 space is T1, and the second part is a product of T1 spaces is also T1, and here product means in product topology. Just note that whenever we talk about the product topology, then that is the product of a topological space, then you always assume that it is a product topology if nothing is mentioned. If there is a box topology or uniform topology, something like that, then there should be mentioned that one. So if nothing is mentioned, then you can always take it as a product topology. Anyway, the proof is the simple, that straightforward proof, but here I am doing that one. So first of all, let X be a T1 topological space and Y be a subspace of X. Now we claim that Y is also T1. So for that we first assume, that is take two arbitrary element from Y. So let X, two element means two different element, obviously, right? So let X not equal to Y in Y, that is the space Y. But we know that Y is subspace of X, right? That's mean that two elements X and Y are also elements in X. But it is given that X is T1. Therefore, there exist open sets, only one open set U containing X such that Y does not belong to U, right? And here open set U means this is open set in X, right? Now that implies X belongs to U intersection Y. Why? Because X belongs to U as well as X belongs to X. Therefore, X belongs to Y as well as X belongs to U. Therefore, X belongs to U intersection Y. And you can say that X does not belong to U. U intersection Y. So why U does not belong to U intersection Y? Because U intersection Y is a subset of U, right? And Y does not belong to U. Therefore, Y does not belong to U intersection Y as well. Now we know that Y is an open set in X. Therefore, U intersection Y is an open set in Y. Now since U is an open set in X, therefore U intersection Y is an open set in Y, and which satisfies the required property, right? Therefore Y is T1. So this is the first part. Now here we move to the second part of the theorem. So let X alpha, where alpha be some index set lambda, be an arbitrary family of T1 space. Now we claim that product of X alpha is T1 in product topology. So how to solve this problem? So we choose two elements from the product. That's mean two distinct element. So let X not equal to Y belongs to this product. Now since X and Y belong to that product, that's mean X is of the form X alpha and Y is of the form Y alpha, right? Now given that X not equal to Y, what does it mean? Since X not equal to Y, that's mean there exists an index beta from lambda such that X beta not equal to Y beta. So it is sufficient to say that X and Y are distinct, right? Now given that X beta is T1, therefore there exists an open set, say U beta, in the topological space X beta such that X beta belongs to U beta and Y beta does not belong to that U beta, right? Now let U equal to that Y beta inverse U beta. So what is my U then? This is just a product of U alpha, where U alpha equal to X alpha if alpha not equal to beta, right? Okay, obviously U is an open set in X. U is an open set in X. Also, it is clear that X belongs to U. Why X belongs to U? Now, since each of X alpha belongs to U alpha, that implies X belongs to U. And since X beta does not belong to U beta, that implies X, so there exists a beta. We can write it is not in the arbitrary. So beta is not arbitrary. Alpha is arbitrary, but beta is not arbitrary for a beta. That implies, sorry, it is not X beta, it is Y beta, right? So Y does not belong to U, right? Now this implies the product X alpha is T1. Here is the second theorem, which will be very useful to compute that a topological space is normal or not. Here is the statement of the theorem. This theorem says a topological space X has a property that the one point sets are closed in X. Okay, then the topological space X is normal if and only if there exists, or if and only we can say that, given a closed set A and an open set U containing A so there exists another open set V such that A subset of V and V closure subset of U. That's mean, in other words, you can say A is normal if and only if for any pair A and U with, that is, A is a closed set and U is open in X, that is, for such pair there exists V, or you can say open set V such that A subset of V and V closure subset of U. That is if and only if condition. That's mean, first of all we assume that X is normal, and then we prove that for any pair of two sets, that is, one is closed set A, another is open set U, such that A subset of U, then we have A open set V such that A subset of V and V closure subset of U. This is one part. And conversely, we will prove that if a topological space satisfies this property, then X is normal. But you have to assume that for this one, that is, this is not only that necessary sufficient condition to show that X is normal, you always have to first show that the singleton point is closed. You have to first show that, and then you have to verify this property. Okay? Now here is the proof. First of all, assume that X is normal. So, do you know the definition of normal? Okay, I can recall that. That is, X is normal if the one property is that one point set are closed in X. So we will not verify this property, right? It is already given. And the second one is for any two disjoint closed sets A and B, that is A intersection B is empty. There exist open sets U and V such that A subset of U, B subset of V, and U intersection V is empty. That's mean if you have a disjoint open closed sets, then they are separated by the open neighborhoods. Okay, now this is the definition of normal. Now we assume that X is normal, that is X satisfies these properties. Now we will prove that then X will satisfy the given property which is given in there. That's mean for any pair A subset of U, there exists a V such that A subset of V and V closure subset of U. So we will find such existence of V or existence of such V. Okay. Now let A be a open set in X and closed U be an open set in X such that A subset of U. Okay. Now we prove that there exists a V which satisfies those properties, right? Now let B equal to X minus U, right? Now note that given that U is open, so B is the complement of U, therefore B is closed, right? Then B is closed in X and A intersection V is empty. Why? As A subset of U and B is just a complement of U. This is clear, right? We have seen these properties in the set theoretic result in the first lecture, that is first lecture of this separation axiom, right? Okay. Now since X is normal, so there exist V, or you can say there exist open sets V and W such that A subset of V and B subset of W and B intersection W is empty. Fine, up to this is fine, right? Note that we have seen last time if two open sets are disjoint, that is if V intersection W is empty and both are open, then V closure intersection W is also empty, right? We have seen that. Now since V and W are open in X, therefore V closure intersection W is also empty. Do you remember the proof of this one? So this is the simple one, right? Because see, V intersection W is empty. That's mean V subset of W complement. Now W is open, so W complement is closed. So V subset of a closed set, that is V complement. Now what is V closure? V closure is the smallest closed set containing V, right? That's mean V closure subset of W complement, right? Therefore, V closure intersection W is empty. Now this part is simple, right? Now since B subset of W, that imply V closure intersection V is also empty, right? Okay, now this imply V closure subset of X minus B, that is B complement. Now what is X minus B? See, B is my X minus U. So what is X minus B? That is U. So we are done. So that implies a subset of V and V closure subset of U. This is the required condition. Okay. Now we move to the next part. It is the converse of this statement. Now assume that converse. Assume that the given condition holds. So which is the given condition? That's mean for any pair of A and U, where A is closed, U is open, A subset of U, you always have one open set V such that A subset of V and V closed subset of U. You have this condition and you have to prove that the topological space X is normal. Therefore, so let A and B be two closed sets in X. Right? So we need to prove that X is normal. That's mean we need to find two open sets U and V, right? Which are disjoint and U containing A and V containing B, right? Okay, so we can write disjoint to disjoint closed sets, right? This is disjoint. Now that imply A subset of X minus B. Why? As A intersection B is empty, right? Now B is a closed set. So what is my X minus B? That is open, right? Now since X minus B is an open set containing A, so by the given condition, so there exists say U or say V, maybe V, there exists open sets V, open set V such that A subset of V and V closure subset of X minus B. Now this imply B subset of X minus V closure. Now V closure is closed in X. Therefore X minus V closure is open in X, right? Now since V closure is closed in X, so X minus V closure is open in X. So let U equal to V minus X minus V closure. Therefore, we have open sets V and U such that A subset of V and B subset of U and U intersection V is empty. Now why this is empty? Now the proof is also simple, or it is easy to see from the picture. So what is my V? So V is subset of V closure. That imply you can write that V intersection X minus V closure is empty. That imply V intersection U is empty, right? So we are done. So that imply X is normal. So this completes the proof of this theorem. So now we prove that every regular space with a countable basis is normal. So the proof of this theorem is little bit tricky. So there are many steps of this theorem. So you have to be very careful during the proof. So here is the statement, that is every regular space with a countable basis is normal. So first of all, we have a regular topological space X which has a countable basis beta. Okay. So here is the proof. So let X be a regular topological space and let beta be a countable basis of X. Okay, now we need to prove that X is normal. That means we have to check two properties, right? What is the first property? So we have to prove that any singleton set, that is any one point sets, is open, is closed, and we have to show that if we take any two disjoint closed set, then they are separated by some open neighborhoods, right? Now the first property is trivial. Why? Because X is regular. Now since X is regular, so one point sets are closed in X, right? So first property is trivial. Now we need to check only the second property. So for that, let A and B be two disjoint closed sets in X, right? And we need to find two open sets, say U and V, such that A subset of U and B subset of V and a U intersection V is empty. So we need to find two such open sets. So this is our job, to find that open sets, right? Now first of all, we have to use the property of regularity and the countable basis, right? Now let X belongs to A. What does it mean? That's mean X not belongs to B. Why? Since A or B are disjoint, right? So as A intersection B is empty. Now that will imply X belongs to X minus V, that is complement of B. Now since B is closed, so X minus V is open. So since B is closed, so X minus B is a open set containing X and disjoint from V, right? That's when X belongs to X minus B and this is an open set. That's all. Now we use the property of regularity. So what do you mean by a space is regular? That's mean if X belongs to, that's a point belongs to an open set, that's mean there exists another open set, say V, such that X belongs to V and a V closure subset of this open set, right? This is the if and only criteria for the regular topological space. Now since X is regular, right? So there exists V, so we can say there exists open set V such that X belongs to V and V closure subset of that open set, right? Now again, what do you mean by X belongs to V? Now since X belongs to V and beta is a basis for the topology, right? That imply, now since beta is a basis for the topology, on X, note that beta has another property. It is not only basis, right? It is a countable basis. Anyway, here we need that only the property of basis. Now since beta is a basis for the topology on X, so there exists Bx belongs to beta such that X belongs to that Vx, which is subset of V, right? Now what are the properties of that Bx? That is Bx belongs to beta has the property that X belongs to A and Bx closure intersection beta is empty. Now why this is true? That is Bx closure intersection B is empty. Why this? Because as now what is my Bx? So Bx closure subset of V closure, since Bx subset of V, and this is subset of x minus v, right? So that implies bx closure intersection v is empty, right? Okay. Now beta dash is just a collection of this kind of bx. That's mean it is the collection of bx subset of belongs to beta such that, or you can write such that x belongs to a and bx closure intersection b is empty. That's mean for each x we get such a bx, right? Now, so this implies beta dash covers a. That's mean beta dash is an open cover of a. So why this covers a? Because here, since here x is arbitrary, right? Here I can take a different pen. Here this x is arbitrary, right? That's mean whenever we have a point in x, we always get such a beta x, and we are taking all of this collection beta dash. That's right. That's mean beta dash covers a. And again, since beta dash subset of beta and beta is countable, that's mean beta dash is also countable. Now you can little bit confused about this one. See, what is my beta dash? Beta dash is a collection of bx, right, where x belongs to a. That's mean you can think beta dash as a, that is its cardinality is same as the cardinality of a, right? But actually this is not true, because since we are choosing element from beta, right, and beta is countable, so beta dash should be countable. That's mean if a is uncountable, then there may be more than one element, say x and y, for which bx and by may be same. So I can note here, so note for two different, say distinct x, y in A, bx and by may be equal, right? So that's mean we can say beta dash is a countable open cover of A. Right? Now since beta dash is countable, so we can think the elements of beta dash as a enumerated, right? That's mean let, so we can say rename the elements of beta dash as u1, u2 in this way. That is beta dash equal to, we assume that u1, u2 in this way. So what is the property of ui? That is beta dash equal to u1, u2, this one has the property that for any element, say A belongs to A, there exists n such that A belongs to un, right? And for each I belongs to natural number, ui closure intersection B is empty. So this is my property of beta dash. Similarly, so by considering B instead of A, we get a collection say beta double dash such that say it is V1, V2 in this way, that is a countable cover of B, right? With the property that so for each I, Vi closure intersection A is empty, and for each B belongs to B, there exists N belongs to natural number such that B belongs to Vn, right? So we can find this kind of beta double dash subset of beta by by doing the same property, just replace A by B and B by A, right? So we can get this one. So up to this part is done. Now observe that, so I can write a different pen, continue with that. So A subset of this union and B subset of union of this one. Now obviously this part is open, this part is open, right? So we get two neighborhood such that A subset of this and B subset of this. But unfortunately this intersect this is not empty, that is may not be empty. This is my problem. Now we have to tackle this problem. So how to tackle this problem, that is their intersection is not empty. Now we find another open sets. How to find another open sets? So here we can write u1 dash equal to say u1 minus v1 closure, say u2 dash equal to u2 minus v1 closure union v2 closure in this way. That is my un dash will be my un minus say v1 closure union up to vn closure. In this way you construct a new set u1 dash, u2 dash, un dash, right? Now similarly we get say v1 dash equal to say v1 minus u1 closure, say v2 dash equal to v2 minus u1 union u2 this, and similarly say vn dash equal to say vn minus u1 closure union u2 closure un closure, and this way, right? Now observe that each of ui dash and vi dash are open, right? So we can write here, since that B1 closure union, that is that finite one, right? Bn closure is closed, so and even is open, so even dash is open, right? And similarly Bn dash is open for all n belongs to natural number. Fine. Now let u1 dash equal to union of that one, that is say n equal to 1 to infinity even dash, say this is my u dash, and v dash equal to union of n equal to 1 to infinity bn dash. Fine. Now we claim that, see, the previously we constructed u and v in this way, right? Now we claim that this u dash and v dash covers a and b respectively, and their intersection is disjoint. So first claim, so we can write it is claim 1. So a subset of u dash. So let a belongs to a. Now we note that what is my beta double dash. Just recall what is my beta double dash. See, beta double dash is a collection of v1, v2, vn with the property that for each I this is empty, that is vi closure intersection a is empty, right? Then that a does not belong to vi closure, as a intersection vi closure is empty for all I. Okay. Now since a belongs to a and that collection u1, u2, u3, that collection, that is the collection beta dash covers a. Now since beta dash covers a, so there exists n such that a belongs to un, right? Now since a not belongs to v1 closure, v2 closure up to vn closure, that will imply a does not belong to their union as well, right? That will imply a belongs to un minus that one, right? That will imply a belongs to un dash, right? So that is a subset of u dash, right? Now claim 2. So b subset of v dash again. So let b belongs to b. Now since beta dash double dash, which is that collection this, covers B. So there exists say N such that B belongs to Vn, right? Also it is given that B say B intersection ui closure is empty for all I belongs to natural number, right? Now that will imply B not belongs to that ui closure for all I belongs to n. That will imply B not belongs to at least B1 up to U capital N closure, right? Now that will imply B not belongs to the union as well. Now since B belongs to Vn and B does not belong to their union, so we can subtract that part. So there is no harm, right? Now that will imply B belongs to Vn minus their this. So B belongs to, that is my Vn dash. So this is subset of V dash, right? Now that imply my B subset of V dash. Okay. So claim 2 achieved. Now what about my claim 3? Now what is my claim 3? Now we have another claim that U dash intersection V dash is empty, right? Now if possible, so there is a X belongs to U1 dash intersection V dash, right? Now that will imply X belongs to U dash, which is my 1 to infinity Ui dash, and X belongs to V dash, which is union of I equal to 1 to infinity Vi dash. Now that imply there exist J and K such that X belongs to U J dash and X belongs to V say K dash. Now first of all, so if possible, say J less than equal to K. Now what is my J less than equal to K? Now then from the definition we have X belongs to Uj dash. Now this is subset of Uj, right? Now on the other hand, X belongs to Vk dash, which is my Vk minus union of I equal to 1 to K Ui closure, right? Now it is given that K is bigger equal to J. That's mean it is actually Vk minus, we can write it is U1 closure union up to Uj closure union Uk closure, right? Now that will imply X does not belong to Uj closure. That will imply X does not belong to Uj, but it is given that X belongs to Uj. So this is a contradiction. So this is a contradiction. Now similarly, if we assume that k is less than equal to j, then also we get a contradiction. Okay, so we can do this one again. Now if k less than equal to j, now we get the contradiction the other way, that is x belongs to vk dash, which is subset of vk, right? That's mean x belongs to vk. Again, given that x belongs to uj dash, which is my uj minus I equal to 1 to j vi closure, right? Which is actually uj minus say v1 closure union up to vk closure, again u1 union up to vj closure, since j is bigger than k, right? Now that will imply x belongs to, that is does not belong to vk closure. That will imply x does not belong to vk. But here we have already got that x belongs to vk. So this is the contradiction. Therefore, so we assume that if possible x belongs to this set, right? So this is not true. That's mean that imply u dash intersection v dash is empty. So thus we get two open set u dash and v dash containing my disjoint closed sets A and V, and their intersection also empty. That's mean x is normal. So thus x is normal. Now this completes the proofs. Now this is the little bit tricky, so you can go through the proofs again. So today I stop here.